Today we will see design of pressure vessel or unfired pressure vessel. After this session, you will be able to design unfired pressure vessel. Let us see what do you mean by pressure vessel. The pressure vessel is nothing but a container or a pipeline for storing or receiving or carrying a fluids, or fluid may be gases also, under a pressure, and this pressure is above atmospheric pressure. Now here unfired pressure vessels are storage vessels, reaction vessels, heat exchanger and evaporators. These pressure vessels are designed on the basis of or using national or international codes. Indian standard codes gives guidelines to design the pressure vessels which are fabricated by using welded joints. And these pressure vessels are made of ferrous material and having pressure range 1 kgf per centimeter square to 200 kgf per centimeter square. As per IS code, we can design such a type of pressure vessels made of ferrous material and having this pressure range. And smaller pressure vessels having diameter less than 150 mm, which are used generally for water tank or containers, and having storage capacity less than 500 are not included under this Indian standard code. You will find again such a pressure, again other pressure vessels such as steam boiler, nuclear pressure vessel, hot water storage tanks are also not included under this IS code. That means here in design of unfired pressure vessel, the pressure vessel which are made of ferrous material, they are fabricated by welding joints and having the pressure range are comes under this Indian standard codes. Now let us see this unfired pressure vessels. Now this is one of the pressure vessel which is shown having different openings and different mountings are provided here to this pressure vessel. Now again these pressure vessel, you will find here different categories of welded joints. Important point here in unfired pressure vessel, that means categories of welded joints. Different welded joints are used while fabricating unfired pressure vessels, but these categories of welded joints are not depends on types of weld, but it depends on location of a joint in a vessel. That means which part, suppose opening or a nozzle or a flanges, how they are joined to this vessel and how this vessel is fabricated. Based on that location of that joint, the welded joints categories are given. There are 4 categories. One is category A, category B, category C and category D. In next slide we will see what do you mean by category A, B, C and D and how they are used to connect the different parts of this pressure vessel. Again in general, you will find materials used for unfired pressure vessels are plain carbon steel, alloy steel, cast iron, aluminum steel, copper and copper alloy, nickel and nickel alloy. These are the materials used for unfired pressure vessels. Now let us see. Here you will find the different categories of welded joints A, B, C, but they depends on their location. Now let us see first category A. Category A welded joint. It's a longitudinal joint within the main cell to fabricate this vessel, and it is also used for communicating chambers and nozzles or joining enclosures to the main cell. See in this diagram. Now here you will find A. It's a longitudinal joint. Longitudinal. This is A. Again here you will find this is used to join some of the parts, that is here suppose nozzle, which is also here. You will find again how it is connected to this vessel. Here it's by circumferential, but again this longitudinal joint to this component, and again it is connected to this, and again here all these longitudinal longitudinally this vessel is fabricated. So that's why longitudinal joint within the main cell. And also use communicating chambers and nozzle. Chambers and nozzle means nozzle and chambers. Again you will find longitudinal joints and they are connected to the main pressure vessel. Then now another category is the B. B means circumferentially welded joints within the main cell. Now look at this. Now here this opening here is circumferentially it is welded here at B. Again you will find here also in another case this B here. Then again all here also. Now suppose take this example. This is the one part and this is the part. How they are joined here circumferentially. This joint is B. Again here circumferentially this is also B. Again this is also circumferentially you will find B. That means it's a circumferential welded joint within the main cell. That means in this way, circumferential, and in longitudinal in this way. Then another third category of the weld joint, that is category C, which is used to connecting flanges, plateheads to the main cell. Platehead means this. Here it is shown by C. Again suppose this is the flange which is connected through the C. Again you will find this part which is C through the C, or this part, this is C. That means another use for connecting flanges or plateheads. And category D is the welded joints connecting chambers and nozzles to the main cell. Now here this is one opening which is joined here by D location. Again here you will find this part also joined here, you will find the weld D or category D. Again here also this part joined to this by weld D. In this way you will find all over the weld D to connect these chambers or nozzles to the main cell. That means the joining of these parts to the main cell. That means these are the welded category of different welds A, B and C. Now come to the next point, classification of pressure vessel. Now pressure vessel classified into three types: class 1 pressure vessel, class 2 pressure vessel, class 3 pressure vessel. Now class 1 pressure vessel is used for poisonous gases and liquids, and these gases and liquids are dangerous to human life. It comes under the class of or class 1. Again, such a pressure vessels are used for lethal or toxic substances, and these toxic substances are hydrocyanic acid, carbonyl chloride or mustard gas. Again, another important points here, operating temperature of this class 1 pressure vessel which is less than -20 degree. Again, while manufacturing or how it is fabricated, during fabrication or welding, double weld butt joints with full penetration and single welded butt joint backing strips are used while fabricating this pressure vessel. And this welded joint is fully radiographed. Fully radiographed means to check the leakage and to avoid the accidents, because it is used for poisonous gases and liquids. That's why welded joint is fully radiographed in class 1. This is classification of pressure vessel class 1. Then second one, class 2 pressure vessel. It doesn't come under this class 1 and class 3. But maximum cell thickness of this pressure vessel, that is up to 38 mm. And here also you will find the double welded joint, butt joint with full penetration and single welded butt joint by backing strip are used in this class 2 also. And even though in class 1 you will find the same type of weld joints, double welded butt joint with penetration and single butt joint with backing strip. Only the difference is here, the wall thickness, they are not used for these toxic or poisonous gases or liquids. And again important one, in class 1 pressure vessel, all welded joints are fully radiographed or checked. But in this case, only in class 2, welded joints is spot radiograph. Then another class 3 pressure vessel. Now here, maximum cell thickness up to 16 mm. Here 38. Then operating temperature is not less than 0 degree, that means more than 0, that means 1, and up to 250, and maximum pressure is limited to 17.5 kg per centimeter square. And these class 3 pressure vessels are used for light duties, and they are made up of carbon and low alloy steel. That means you will find categories of welded joint, that is A, B, C, D, their relevance, how they are communicating the different parts, and how they are fabricating the pressure vessel. Classification of pressure vessel, 3 classes: class 1, class 2, class 3, and which class 1 is used for which type of gases or fluids, class 2 again how it is checked safety point of view, and class 3 for light duties. Now again look at this. Now here you will find in class 1 and class 2 double welded butt joint with full penetration. This is butt joint. And fully radiograph. If it's a fully radiograph, the weld joint efficiency you will find 1 means it's in the 100%. Spot radiograph 0.8. Suppose in class 2 spot radiographed for double weld, that means we have to consider weld efficiency 0.85, and not radiograph that time 0.7. Then single weld butt joint with backing strip. Here this is the strip which is used for this butt weld. That time fully radiograph efficiency is 0.9 or 90%. For spot radiograph 80% and non-graph 0.65. And similarly single welded butt joint without backing strip. Here strip is provided, it is not provided here. The efficiency 0.60 or 60% for non-graph. And weld efficiency means ratio of weld strength of the weld joint to the strength of the plates. Now again here all these pressure vessels are fabricated by using which welding process? Fusion welding process. Fusion means fusion of the two metals, and for that purpose different weldings are used: arc welding, gas welding, thermite welding, electron beam welding. Then the weld efficiency depends on, here you will find when it is fully radiograph you will find 100%. The method of inspection, that is important, and second one is the type of the weld. Look at this. Why type of the weld? Because it is double butt joint, fully radiograph 100%, but single butt weld with back strip, and even though fully radiograph it's 90%. That means weld efficiency depends on type of weld and method of weld inspection. Now here in design, the important parameters plays role. Now let us consider these important parameters for unfired pressure vessel. The first one is maximum working pressure. While designing the pressure vessel, you have to use this word many times: maximum working pressure. Maximum working pressure means this is the pressure required for the processes that carried out inside the vessel or permitted for the vessel when it's in operation. That is maximum working pressure, that is Pmax. This is one parameter. Then another parameter is the design pressure. Design means while designing the pressure vessel, actually we are going to consider this pressure to find out the sail thickness or other dimensions or design of other component, that is nozzles and openings of the pressure vessel. That is design pressure. That means we are going to use this design pressure vessel. But this design pressure, value of design pressure vessel is taken 5% more than the working pressure, and that's why this PI becomes 1.05 of Pmax. And another term, hydrostatic test pressure, that is PB. Hydrostatic, that means pressure vessel is tested after manufacturing by the hydrostatic test, and this hydrostatic pressure is taken as 1.3 times the design pressure, 1.3 multiplied by 30% more. So that's why you will get PB is equal to 1.3 into design pressure. Now here by using design pressure, it is 5% more than the working. We can find out the dimensions of sail thickness, and that we have to use hydrostatic pressure just to check the pressure vessel, and maximum working pressure means the pressure required to carry out the process inside the vessel, that is maximum working pressure. Now design of unfired pressure vessel. This is important. How to design the unfired pressure vessel. Now first of all, find out the thickness of the pressure vessel. Now here consider it. It's a open air cylindrical pressure vessel having the length L, the diameter is D, inside diameter suppose Di, having thickness T, or min. Here in this case capital D is considered the min diameter, that's why Di plus T. Now consider the equilibrium of vertical forces. The same logic already we have used in earlier sessions, the design of thin cylinder. Now here the same method we are going to use based on the thin cylinder. Now considering the equilibrium of the forces. Now these forces are circumferential stresses. The Pi into D into L is equal to sigma T into 2 into thickness into length L into efficiency. Again here arranging the terms we can find out the T here, but before that what we have to do, sigma circumferential or tangential we can shift to sigma allowable, and this D min diameter is equal to Di plus T. Substituting these values we will get T is equal to Pi into Di upon 2 into sigma allowable into efficiency minus Pi. Pi means internal pressure. Again here what is happening, we have to add corrosion allowance. Why corrosion allowance? Inside the pressure vessel the chemicals, there is a reaction or oxidation. It's because of that erosion of the pressure vessel may takes place, and that's why this corrosion allowance is added to this equation. That's why this equation is further modified for cylindrical cell. T is equal to Pi Di upon 2 sigma allowable efficiency minus Pi plus CSA is the corrosion allowance. And similarly, by using the theory of spherical vessel, thin spherical vessel, we can find out the thickness which is given by the expression T is equal to Pi Di upon 4 sigma allowable into efficiency minus Pi plus Ci. That means this equation of thickness is applicable to spherical vessel, and this is for cylindrical, that means this vessel, based on thin cylinder concept. Now here allowable stresses. What is the value of allowable? As per IS code, sigma allowable is equal to SE2 by 3. Sigma allowable as per SME code SE2 by 4. And as per the DIN Deutsch standard, sigma allowable is equal to SE2 upon 1.5. Now here as per our definition 3, 4, 1.5 are the FOS. But as per the code they are given, that's why we are using these values, but don't consider it's a factor of safety. For that purpose in different codes the standard allowable or values of these stresses are given, that we are to use it. Again here what is the value of corrosion allowance? The minimum corrosion allowance that is to be added, that is 1.5 mm. And why 1.5? Because this corrosion allowance is because of why provision is made, because thinning of the wall due to corrosion, and that's why to increase the thickness of the cylinder wall we are going to add this by 1.5. That's why in this expression you will find a corrosion allowance, here also corrosion allowance, to take the care of thinning of the wall due to corrosion. Now again here, that means by using this expression we can find out the thickness of this cylinder and thickness of the spherical vessel. Now again here what we have to do here, the pressure vessel is subjected to combine another loading. So that's why we have to consider these other loads on pressure vessel while designing it. Now here these another loads are, first one is to weight of the vessel with its contents, because pressure vessel is having some thickness, material is used having some density, the weight of that vessel also we have to consider. If it's a horizontal vessel which is filled with some gas or liquids, that weight also we have to consider. If it's a vertical vessel, and supports are given here, we have to consider weight of that vessel with content also. That's why other loads on pressure vessel means weight of the vessel with its consent. Second, if it's a horizontal or a vertical, accordingly wind load, as the because of this wind, as the air flows, we have to consider its effect by taking into account wind load. And third one, the pipings or openings are connected. It is not at the at coaxial position. They are located anywhere on the pressure vessel, and because of that load, because of this offset piping, that also we have to consider. And because of this, some stresses are going to induce in it. These stresses we have to find out and check out whether they are within the permissible limit or not. If they are within the permissible limit, we can say our design is safe. Now let us consider the first one. Stresses induced in the cylindrical vessel due to combined loading. Because of this combined load, now we are going to consider all these things here. Combined loading, the stress induced in circumferential or tangential direction, which is calculated by, we know that this is the equation applicable for thin cylinders. Stress in circumferential direction sigma t pi d upon 2t, but d is the mean diameter, which is given di plus t. By using this expression, we can find out stress in circumferential or tangential direction. Then again, second stress in longitudinal or axial direction. But while finding out it, you will find this is longitudinal stress. This is because of due to internal pressure. Again, this longitudinal stress, this is due to the weight of the vessel and its content, and because of the bending stress because of the total weight. That means we have to take the care of this. While calculating longitudinal stress, we will get the three magnitudes: sigma L1, sigma L2 and sigma L3. Sigma L1 because of the internal pressure, sigma L2 because of the weight and its content, and sigma L3 because of bending stress due to total weight. That means we have to find out this sigma L1, sigma L2 and sigma L3 to get the value of longitudinal sigma L. Now let us consider longitudinal stress due to internal pressure, that is sigma L1. The longitudinal stress, already we have derived this expression in earlier session, pi di upon 40. By using this expression, we will get sigma L1. Now let us find out sigma L2. How to find out? Now here in this case, what we have to do? We have to consider the stress in longitudinal direction due to weight of the vessel and its content in vertical pressure. Now this is the vertical pressure vessel. Now it is, if it is filled with some the liquid or gases, it weights act up to these points. You will find here one line is drawn. Above this B, it is subjected to this compressive stress zone, and below this B you will find here at this where the supports are fitted to this vertical, you will find the bottom part is subjected to tensile stresses and the upper part is compressive. Compressive means because of the load as well as the weight of the pressure vessel. And now this sigma L2 longitudinal stress, that means in this way along this axis of the vertical pressure vessel, plus minus W upon area, this pi into D into T. Again this capital D means Di plus T. That means by using this expression, W is the weight of the vessel plus weight of the content inside it. That means weight of the vessel. How to find out the weight of the vessel? The mass upon volume is equal to density. The first of all find out mass upon volume. First of all we have to find out the volume. This is cylindrical part. Again this is hemispherical part. That means we have to add this cylindrical part volume plus hemispherical part volume plus this mass upon volume is equal to rho. Density of this material, you will get mass. This is the weight of the vessel. And second, weight of the content inside it. Again content is having some density, or that material is having density. Again we can find out the weight of that content also, and adding this weight of the pressure vessel plus content weight, you will get this W, and you will get sigma L2, that means longitudinal stress. Then again find out sigma L3. This is bending, this L3 depends on the bending stress due to total weight. How to find out this sigma L3? M upon Z or MB, sigma B is equal to MBY by I. Again, Z is the section modulus. We can find out Z is equal to I by Y. Substituting these values, dO by 2, then Ixx means pi d by 2 bracket cube into t. You can substitute all these values, you will get Z is equal to pi in bracket di plus t bracket square into t upon 4. Di means inside diameter, t is the wall thickness, again thickness by 4. So you can find out here Z. Now what's about the M that we have to find out, and this M depends on whether the pressure vessel is vertical or whether the pressure vessel is horizontal, and for that we have to find out this bending moments, and after substituting this you will get the sigma L3. Now let us see how to find out M. Now here suppose this is the horizontal pressure vessel. Now here this cylindrical sail having the length L, and after that this end closures having the length that is our height H, and its distance from the support is A. By using this nomenclature A from this peaks to the up to the cylinder, or the cylinder length is the L and the end closures here H. By using this we can find out the bending moment in a horizontal pressure vessel cell, that is Wt by 16 in bracket d square plus 2l square minus 4h square upon L plus 4h by 3 minus 8a. A means this distance, H means this distance, end closer, end to up to the cylinder, this, and L is length of this cylindrical cell up to this. By substituting all this value, and Wt is the weight of the pressure vessel and its content, so you will get this M. You can substitute this M here. We know the Z, you will get the sigma L3, but this is applicable to horizontal. Similarly, if pressure vessel is vertical, what to do? If it's vertical, look at this. Now in this case you will find it is mounted on the ground. Again from this x distance here we are going to find out the bending moment. Now here you will find this pressure is P1, this is P2, and again what we have to do, because of the wind flow, this H1 is the height we have to consider for the bottom of this pressure vessel, or force due to wind load acting on lower part, this H1, and this H2 for upper part, force due to the wind load acting on the upper part. How to find out it? Now here this bending moment acting on vertical pressure vessel because of this wind flow, which is given by, suppose Fw1, this is for the bottom one. Now here again what we have to do, from this x, the H1 is the total minus this x by 2, so you will get this term, plus the Fw2. What is Fw2? Force due to wind load which is acting on the upper part of the sail. Barabar? In bracket H1 minus this H1 minus x, that we are going to take the value from this x, that's why subtracting x, plus this H2 by 2, the Fwt in bracket H1 minus x plus H2 by 2. By using this expression, or we have to take the bending moment as usual. You can consider all these are the forces, this is the length, and find out the bending moment. Already you studied in strength of machine element, and after finding it you will get the MW. This is for this case. Again here what is the magnitude of this Fw1? Fw1 means force due to this Fw1, force due to the wind load acting on lower part, and which is given by P1, this P1 into this DO is the diameter of this cell, into the H1 minus x, which is acting here. We have considered from this x, that's why H1 minus x. And what's about the Fw2? This is also a force due to wind load acting on upper part. How to find out this? The P2 into this H2 and into DO. Now in this case, why this H1 minus x is considered? Because we are considering the wind effect above this x, that's why we have considered H1 minus x. If we are going to consider from the effect from the bottom side, then you will get H, instead of H1 minus x, it should be H1, but effect is above the ground level from a distance this x, that's why H1 minus x. Again here the value of this P1 and P2, that is wind pressure in standard value is given up to the sail height, that is 20 meter, 4.623 into 10 raised to minus 8 into VW square, or after sail height 20 meter, that means after 20, as the height increasing, the P2 value 4.63 into 10 raised to VW square, and VW square is equal to wind speed in kilometer. Now in this case we have to see here the value of this, both the cases, up to this and up to this, we have to substitute this value. You will get the FW1, FW2, again substitute here MW or bending moment, or even though you can use the fundamentals of here, fundamentals of strength of machine element considering the length, and find out the bending moment. Now this is for wind load. Another case here, seismic load. For seismic load again, so you will find this load which is more at the top portion. Again total height is h, its effect is above this x. Consider it's a varying load condition and find out the bending moment. Find out the bending moment. And out of these two, wind level versus kick load condition, which one is the maximum, that M from this vertical pressure vessel we are going to use to find out the sigma B, that is M, maybe MW or MS. Out of this, which one is the maximum divided by Z gives the bending moment for this vertical pressure vessel. And after getting this sigma L1, sigma L2 and sigma L3, we can add all this, you will get the longitudinal, total longitudinal stress. Then third case, some of the pipes which are offset, they are not at the collinear with the axis of the pressure vessel, and because of its pitting or because of this offsetting, torsional shear stresses are induced, and which is in general expression tau by R is equal to T by J, where tau is the torsional shear stress is given by this equation, as usual simple equation. But here we can find out here, substituting the values, the tau is equal to 2t upon pi d square into t, and where d is the di plus t, you can substitute. That means by using this equation we can find out the torsional shear stress due to offset piping. Now we have sigma t, we have sigma L and tau. Again at the last, to find out the resultant test, what we have to do, use the distortion energy theory, and therefore according to this theory, resultant stress is equal to under root sigma t square minus sigma t into sigma L plus sigma L square plus 3 tau square. Substitute this tau here. Sigma L means sigma L1 plus sigma L2 plus sigma L3, that is sigma L, and sigma t means circumferential or tangential stress here, already calculated. You can substitute here and check this resultant stress should be less than the sigma allowable for the given application, and then you can say, or this all these values should be less than the allowable, or it should be within the limit, then and then you can say your design is safe. That means in this way, by calculating the circumferential stress, longitudinal stress and bending or torsional stress, we can find out the resultant stress induced in it while designing it. So what care you have to take while designing it? First of all, find out the pressure vessel thickness. This is for cylindrical. Again we have to learn one topic is remaining, that is about the different heads or closures are used having different shapes, and that how to find out their thickness, that we are going to learn in next session. That also we have to find out while designing this unfired pressure vessel. First of all, find out this thickness, whether it's a cylindrical vessel or a spherical. Then second, find out the stresses because of this combined loading, and because of this combined load, what is going to happen, stresses in circumferential direction, that induced stresses that you have to find out, stresses in longitudinal direction that you have to find out. Longitudinal stresses may be because of internal pressure, maybe because of the weight and weight of the content, and because of this bending stress due to total weight. And third one, that is torsional shear stress. After getting all these values, find out resultant stress. I have referred V.V. Bandari's book and some of the notes available from Arvi Patil's book. Thank you. If you have any query, you can contact me at 9890426679 or mail me at pbkushare@kkwork.edu.